apply is equal to 0. So therefore, when t is equal to 0, mu t is equal to mu 2 minus dash by mu 1 dash whole square is equal to lambda we are taking here. In the similar mu 3 dash is equal to lambda cube plus 3 lambda square plus lambda. Mu 4 dash is equal to all the values are came lambda power 4 plus 6 lambda cube plus lambda square plus lambda. Using them we can find mu 3, mu 4 and b1, b2. So accumulating generating function we can do here. What is the accumulating generating function? If x equivalent to p lambda, then the accumulating generating function here kxt log mxt is equal to log e power x minus lambda 1 minus e power t. So minus lambda 1 minus e power lambda, we can write here lambda 1 minus lambda e power t minus 1. So expansion, this one lambda e power t minus 1 we are expanding here 1 plus t square by 2 factorial t cube by 3 factorial t power 4 by 4 factorial and so on minus 1 we are taking here. Again lambda here I'm multiplying 1 plus t by 1 plus t 1 into t. So this is t plus t square by 2 factorial 1 t cube by 3 factorial and so on. Here we are taking here from the above equation. But the coefficient of t is equal to lambda is equal to mean of the k2 variance coefficient of t square by 2 factorial lambda, k3 coefficient of t cube by 3 lambda is equal to mu 3, k4 coefficient of t4 by 4 factorial lambda. The k1, k2, k3, k4 is we are finding the coefficient variance coefficient and coefficient of this one. So coefficient of t power 4 by 4 factorial we are taking mu power 4 is equal to k power 4 plus 3 k2 square is equal to lambda plus 3 lambda square. Beta 1 is equal to mu 3 2 square by mu 3. Mu 2 cube is equal to mu 4 by mu 2 is equal to 3 by 1 plus lambda we are taking here. So therefore PS is equal to e power Sx we are taking here the probability generating function x equals to p power lambda. Probability generating function, you know that e power minus lambda summation of x is equal to 0 to infinity lambda is whole power x factorial. E power minus lambda 1 plus lambda is whole square by 2 factorial, lambda is whole cube by 3 factorial and so on. So therefore automatically we can write here e power minus lambda. So we can write here e power lambda is e power minus lambda 1 minus s. We can write here these one. So characteristic function. What is the characteristic function we are taking here? So x equal to p lambda, and it's a characteristic function phi of x is equal to e power itx. Summation of x is equal to 0 to infinity e power itx. E power minus lambda. Already I told e power itx. E power minus lambda x e power lambda. E power minus lambda summation of x is equal to 0 to infinity lambda into e power it by x factorial by whole power x. So e power minus lambda into e power lambda it. So e power minus lambda 1 minus it we can write in using the relationship between the characteristics functions here. The function we are taking here only mu1 dash r is equal to 1 by t power r by d power r by dt r lambda phi of x is equal to t is equal to 0. Mu1 dash is equal to lambda mu2 dash is equal to lambda square plus lambda mu2 dash is equal to lambda cube plus 3 lambda square plus lambda mu dash 4 is equal to lambda 4 6 plus 6 cube lambda plus 7 square lambda. Already we finding these values. Through them we can find the central moments beta 1 beta 2 coefficients also here. Then what is the additive property of Poisson distribution we are taking here? So x equivalents to p lambda, x equivalents to p lambda 1 and y equivalents to p lambda 2 are independent Poisson varieties. Z is equal to x plus y. And phi of 2 is equal to phi of x plus phi t, phi of x t, phi of y of t. Since x and y are independent, so e minus 1 1 minus t, e minus 2 1 minus t. So in the powers are we are taking here e power minus of lambda 1 plus lambda 2 of 1 minus it, lambda 1 plus lambda 2 minus taking common here. This is lambda 1 plus lambda 2 vacant, which is a characteristic function of the Poisson distribution with the parameter lambda 1 plus and lambda 2. If general x equal x equal p lambda if independent I is equal to 1 2 k at the 1 2 3 4 k, we are taking the values here. Summation of I is equal to 1 to k. X1 is equal to x1 plus x2 plus x3 plus x4 and so on. Xn is a Poisson parameter. Poisson parameter is lambda 1 plus lambda 2 plus lambda 3 and so on. Lambda, the difference of two independent variates are Poisson variate. So therefore we are taking that xi is equal to 1 2 Therefore, the independent of summation of k is Poisson parameters. We are taking the Poisson distribution, that is I is equal to 1 to k here. Then what is the recurrence relations? What is the recurrence relation? Recurrence relation for Poisson probabilities here. So if equivalent p lambda, then p of x is equal to e power minus lambda x by x factorial lambda greater than 0 x is equal to 0 1 2 px plus 1. So e power minus lambda x power plus 1 by x plus 1 whole factorial. సో అంటే మనం ఏం చేస్తున్నాం దాన్ని p ఆఫ్ x ప్లస్ 1. సో p ఆఫ్ x ప్లస్ 1 x ప్లస్ 1 ఇక్కడ కింది తీసుకొస్తే p ఆఫ్ x ప్లస్ 1 బై p ఆఫ్ x ఈ వాల్యూని తీసుకొస్తున్నాం ఇక్కడికి. సో e పవర్ మైనస్ లాంబ్డా బై లాంబ్డా పవర్ x ప్లస్ 1 e పవర్ మైనస్ లాంబ్డా బై, సో క్యాన్సిల్ అయిపోతే లాంబ్డా బై x ప్లస్ 1 గా మనకు వాల్యూ మిగలడం జరుగుతుంది. p of x plus 1 is equal to lambda by x plus 1 p of x is equal to 0 1 2 with p of 0 e power minus lambda గా మనం రాసుకోవడం is the recurrence relation for Poisson probabilities గా మనం చేసుకోవడం జరుగుతుంది. So recurrence, what is the recurrence relations what we are taking here? So recurrence relations for central moments, px equivalents to then the orth central moment mu r x minus ex x minus lambda whole power r into px p of x is equal to summation of x is equal to infinity x minus lambda whole power r e power minus lambda to lambda x factorial d by d lambda mu r is equal to summation of x is equal to 0 to infinity 1 by x factorial 1 by x factorial x factorial. So d by d lambda we are derivating the function mu r summation of x is equal to 0 to 1 by x. So this is the orth we have to write here, r into r minus 6 lambda minus 1 into e power minus lambda into lambda power x. Again x minus lambda whole power of this is simplification, e power minus lambda x minus lambda whole power r e power lambda x into lambda r power minus 1. This is a simplification of this recurrence relation of central moment minus r mu r minus 1 plus 1 by lambda by mu r plus 1. We can write here this equation. So this is the central moment for mu r minus 1 r into mu r minus 1 plus d by dr mu r. So this is the mu 0 is equal to 1 and mu 1 is equal to 0. Substituting in the above equations here, mu 2 is equal to 1 by 1 into mu 0, mu 3 is equal to 2, mu 4 is equal to 3. So d by d lambda 1 by 1, d by d lambda mu 2, d by d. So that is the total condition is lambda mu 3 lambda plus 1 is equal to lambda plus 3 lambda square of the recurrence relation function we have to do here. Recurrence relation for moments about origin also we can take here. X equivalent to p lambda, then the ith moment about origin is mu dash r e x power r is equal to summation of x is equal to 0 infinity x power r p power x summation of x is equal to 0 to infinity x power r e of minus lambda x by x factorial. d by d lambda mu r dash summation of x is equal to 0 to infinity x power r by x factorial. So minus of e power minus lambda power x plus e power minus lambda, what we are taking here, e power minus lambda power x by x factorial. So the condition, what is the recurring relations of the moment generation, e minus e power minus e power of minus lambda e power minus lambda into lambda power x minus 1 we are taking here using mu dash is equal to 0 1, mu 1 dash is equal to lambda, mu 2 dash is equal to lambda plus 1, lambda square plus lambda, mu 3 dash is equal to lambda square plus lambda, this d by d lambda square plus lambda is equal to lambda cube plus 3 square plus lambda. You can write here mu dash 4 is equal to lambda cube plus 3 lambda square plus lambda plus d by d lambda cube plus 3 lambda square plus lambda. So multiplication is lambda power 4 6 lambda cube plus 7 lambda square plus lambda here. Then the beta 1 beta 2 are coefficients. Mode of Poisson distribution. What is the mode of Poisson distribution we are taking here? X equivalent to p lambda, we have p of x minus 1. Here the Poisson distribution e power minus lambda to lambda power x by x factorial. That is e power minus lambda x power minus 1 by x minus 1 factorial by is equal to lambda by x. Case 1, lambda is positive integer, then p1 by p0 greater than 1, p2 by p1 greater than p3 by p2 greater than 2. So therefore pm by pm minus 1 is equal to 1. So there is a condition pm plus 1 by pm less than 1, pm plus 2 by pm plus 1 less than 1, Pm plus 3 by Pm plus 2 less than 1. So the condition should be satisfied. The M conditions is less than 1. The 1 condition, 2 conditions are greater than 1 and 2. We are taking here. P less than P0 less than P1 less than P2 less than, so Pm minus 1. Pm less than Pm plus 1 less than Pm plus 2 less than, and so on. In this case, the distribution is binomial. Binomial having modes x is equal to m minus 1, x is equal to m. Again, case 2, if m is equal to m plus f, where m is a integer, positive integer, 0 less than f less than 1, we are taking here p1 by p0 greater than 1, p2 by p1 greater than 1, pm by pm minus 1 greater than 1. So that is the condition. Pm plus 2 by pm plus 1 less than, exact reverse. So p0 less than p1 less than p2. There is a case 2, lambda is equal to m plus y. Then the in the case the distribution having the mode x is equal to m, we are taking here. Example we are taking here. Poisson distribution has mode x is equal to 1 and x is equal to 2. What is the probability that x will have one or other of these two values? X is equal to lambda is equal to p, x is equal to 1. So either here they given e power minus 2, they given here e power minus 2 by 2 factorial. So for 2 power factorial by x is equal to 1 factorial, they given by, we are writing here. So e power minus 2 factorial means lambda is 2 square by 2 factorial. So by x is equal to 1, x plus 2 e power minus 2 into 2 square, that is to 4. So they are valuing e power minus 2 of 4, that is 0.542. We are writing here. In a mass production of process, 0.1% of the articles produced and defective. They are the packed boxes of 1000. Find the proportion will contain 2 or more defects. So aim defects should not choose them. Probability in items defective 0.1%, p is equal to 1 by 1000. Number of items is n is equal to 1000. So x is equal to np is equal to 1. Let x be number of defective unit in a box, x equal to p lambda. X greater than to 1 minus probability x is equal to 0 when probability x is equal to 1. So therefore 1 minus probability of x is equal to e power minus 1. X is equal to 1 is e power minus 1 into 1. So e power minus 1 is 1. E power minus 1 is minus 2 by e. So that is a formula of point. That is a simplification of that 1.2642. Automatically we can continue the same. Suppose it is observed that an average of 180 car per hour has passed a specified point on particular road in the morning such rush hour. Due to impending road works, it is estimated that congestion it will occur closer to the city center more than 5 cars of the point 31 minute. What is the probability of congestion of occurring? Let x denote the number of vehicles passing the given point. Let x let x be denote the number of vehicles passing the given point here. Average number of vehicles. Average number of vehicles we are taking here 180 by 60, that is 3. So 60 by 180 is equal to 3 minutes. So x equivalent to p lambda by 3. So we p x greater than 5, we are taking 1 minus summation of x is equal to 4. So what is the formula? 1 minus e power minus 3. So we are taking here 1 plus 3, that is condition 1 plus 3, 3 square by 2, 3 cube by 6, and 3 power 4 by 24. 5 becomes x greater than 5. X greater than 5 కాబట్టి 4 వరకే తీసుకోవాలి. So 9 by 2, 27 by 6, and 81 by 24. These values are getting here 0.8147. We are taking this one. So discrete uniform distribution, mean variance, moment generating function, probability generating function, characteristic function. The problems you are taking here. In this unit, we will study the probability mass function and discrete uniform variant, its mean and variance, its moment generating function and characteristic function also we can learn here. When the different events associated with the experiment have an equal chance occurrence here, we find the application of discrete uniform distribution. For example, if a pair dice is thrown, all the 6 faces in equal chances to win. Discrete uniform distribution definition. A discrete random variable x is said to be uniform distribution. 1 to m is a probability mass function. P of x is equal to m, x is equal to 1, 2, 3, and so on m. 0 otherwise here. When a pair dice x is thrown, x denotes number of turned up, then px is equal to 1 by 6 is equal to 1, 2. A box contains here 10 balls which number serially 1 to n. If x denotes the number of ball selected random from the box with replacement, p of x is equal to 1 by x is equal to 1 to 1 by x and x is equal to 1, 2, 3, and so on. N we are taking here. Properties of uniform distribution we are taking here. So mean and variance. If x has a uniform distribution of the integers 1, 2, 3, 4, 5, 6, 7, and n. So on the first moment about the origin is mu1 dash is equal e of x, if e of x is equal to x is equal, summation of x is equal to 1 to n x dot p of x 1 by n. So 1 by n, 1 plus 2 plus and so on. 1 by n, 1 plus 2 plus 3 plus and so on plus. N plus 1 by 2. The second moment origin is mu2 dash is equal e of x square is equal e of x square is equal summation of x is equal to n x square p of x 1 by n, that is some mu dash is equal to 1 n into n plus 1 by 2. This is 1 by n 1 by n 1 square plus 2 square plus 3 square, that is n into n plus 1 by 2 n plus 1 by 6. Variance mu2 dash is equal to mu1 dash whole square, that is n into 2 n plus 1 by 6 minus n plus 1 whole square by 4. The output condition is n plus 1 into n minus 1 by 12. Moment generating function. If x has a discrete uniform distribution over over the integers 1, 2, 3, n, and then its moment generating function m of xt into e power I tx summation of x is equal to 1 m e power tx 1 by n. So 1 by n e power, that is expansion e power tx plus e power 2t and so on e power mt 1 by n e power 2t minus 1 minus e power nt by 1 minus e power t. 1 by n e power t 1 minus e power nt by 1 minus e power t e power t minus e power n plus 1 by t by n into 1 minus e power t for t not equal to 0. Probability generating function. When x has a discrete uniform distribution over the integers 1, 2, 3 and so on, n probability generating function. So we are taking p of s is equal to e power s of x, summation of x is equal to 1 s power x. అంటే summation of x is equal to 1 to n తీసుకుంటే దాన్ని x power x తీసుకుంటే మనం 1 by n తీసుకుంటాం. 1 by n తీసుకున్నప్పుడు s square s cube and so on s power n దాకా తీసుకుంటే so 1 by n is equal to s into 1 minus s power n by 1 minus s. 1 by n. So simplification s into 1 s minus s power n plus 1 by 1 minus s power s not equal to 1. characteristic function. If x has a discrete uniform distribution over the integer 1 to n, the characteristic function is phi of x as e into e power 80x. Summation of x is equal to 1 to e power 80x into 1 by n. So 1 by n we are taking the common here, e power 80 e power 80 n plus 1 by 1 minus e power 80, that for 80 is equal to 0. So this is the probability, what is the functions and the probability generating functions. We are taking this one. So they define the discrete uniform distribution we are taking here in the usual situations when the events are the equal chance of occurrence here. Then x has uniform distribution here 1, 2, 3, so on n, mean n plus 1 by 2, variance n plus 1 n minus 1 by 12 n square minus 1 by 12. Moment generating function m of x is equal to e power t by minus e power n plus 1 by t by n into n minus 2 for not t not equal to 0. Probability generating function p of s 1 by n s minus s plus 1 s power n plus 1 by 1 minus s for s not equal to 1. Characteristic function also phi of x t is equal to 1 by n e power t minus e power t n plus 1 by 1 minus e power it. We are taking this one in the this one. In the second, discrete distribution too, the study concept of discrete distribution, learn the definition of moment generating function, cumulative generating function, negative binomial distribution, and another unit introduction geometric distribution, derives in moments, hypergeometric distributions we have to learn in this unit. Moment generating function NGF of negative binomial distribution, equivalent of negative binomial distribution, probability generating function of negative binomial distribution, recurrence relation, limiting case of the negative binomial distribution we have to learn in this unit. Define the binomial distribution and MGF or negative binomial distribution and cumulative of distribution we have to learn in this unit. This is the introduction part. So in the probability, suppose we have to take the n Bernoulli trial. We assume that the trials are independent, where the trials are independent here. The probability of success P is the trial remains constant and trial to trial. So let x r comma p, let x r comma p denote the probability that the x values preceding. So in this unit we are already told the screen will be see here. R comma p denote the probability that the x values proceeding the R success in the x plus R trials. Now the last trial must success towards the probability of speech. Remaining x plus R minus 1, we must have R minus 1 success, whose probability given by x plus R minus 1, R minus 1, p power R minus 1 of q power x. By compound the probability theorem, f of x r comma p, given the product of these two probabilities x plus R minus 1, so R minus 1 p of R power minus 1 q of x. So p is equal to x plus R minus 1, R minus 1, p power R q power x we are taking here. We are taking the one definition here. A random variable x is said to be for a negative binomial distribution its probability. Mass function p of x is equal to p of x is equal to x. This is x plus R plus 1, x plus R minus 1, R minus 1. P of p power R q power x is 0 is 1, otherwise the condition we are taking here. X plus R minus 1, R minus 1. X plus R minus 1, this is x. So NCR is equal to NCR is equal to NCN minus R we are taking here. X plus R minus 1, x plus R minus 2, x plus R minus 3, and so on. R plus 1 R. X factorial we are taking here. minus 1 whole power x minus r. We are taking the minus r by minus r minus 1 and so on. Minus so on minus r minus x plus 2 minus r minus x plus 1. So we are writing here minus 1 whole power x minus r c x minus r x minus r minus r c x minus 1 minus n factorial by n minus 1 factorial into n minus r factorial into r factorial. We have to writing here. So p of x is equal to minus r x minus r x p power r minus p power x 3 x 0 1 to 0. Otherwise, which is the x plus 1 whole power, the term expansion p power r minus 1 minus q whole power by the binomial expansion with the negative index. Hence the distribution known as the negative binomial distribution also. P of x greater than 0, summation of x is equal to 0 to infinity. P of x is equal to summation of x is equal to 0 to infinity. Minus rx p power r minus cube x. P power r summation of x is equal to 0 to infinity. Minus rx minus q power x is equal to p power r 1 minus q. And x place of p 1 minus q power minus r p power r into p power minus r. So p plus q is equal to 1. The condition p of x is the probability of function. The discrete random will follow the probability function is called as negative binomial variate here. P is equal to 1 by q and q is equal to p by q. So that q minus p is equal to 1. So p of x is equal to minus rcx into minus rcx minus rx q power minus p minus p by q is equal to x equal to 0 1 to. Otherwise, is the general term in the negative binomial distribution q minus p x. In the negative binomial, p of x also represented all f of x r comma p. The word negative binomial is associated with the distribution because the probability is given the various terms p0, p1, p2, p3 and so on are those expansion p power r 1 minus q. The binomial distribution law values in f of x comma r comma p lo this one that it is a negative index that is called as negative binomial distribution. Moment generating function of negative binomial distribution. The x random variable there is a moment generating function mgf m of x is equal to e and e power itx summation of x is equal to 0 to infinity e power tx. X is equal to where p of x is a probability mass function of negative binomial distribution. So it is a probability mass function PMF is given by minus rx q power minus r minus q by q x is equal to 0 1 2. Otherwise we are taking here m of x t sum of x is equal to 0 to infinity e power tx minus r by x q power minus r minus p by q whole power r we are taking here. So therefore అంటే ఆ సమ్మేషన్ ని మనం rcx లో తీసుకుంటే x is equal to 0 to infinity minus r by x q power minus r minus p into e power t by q by x. So m of x is equal to q minus p into e power t by my q by minus r. The same we are taking here. The moment generating function establish the moment generating about the origin 0 0 0. Now we define with respect to t is equal to 0. d by d of m of x d by dt m of x లో q minus pe power t whole power minus r t is equal to 0. So therefore minus r ని మనం derivation లో d by dt derivation లో మనం బయట తీసుకుంటే minus r q of minus e power t r minus 1. So 0 minus pe power et is equal to 0. So minus r q minus pe minus 0 whole power t minus 1. So 0 minus అంటే దాని డెరివేషన్ పార్ట్ కింద తీసుకొచ్చినట్లయితే minus r q minus p into minus p, therefore r is q minus p is equal to 1 కాబట్టి mu 1 dash is equal to rp. So mean of the negative binomial distribution is mean of the negative distribution is rp. Mean of the negative binomial distribution is rp. Mu 2 dash is equal to d square by dt square m of x t d by dt of m of x t, and d by dt again r into e power pt q minus pet by whole power r minus 1, therefore t is equal to 0. r into e power t derivation తీసుకుంటే q of e minus then r into e power t minus r minus 1. So differentiation చేస్తూ పోతున్నాను నేను దీన్ని ఇక్కడ. So r into e power 0 q minus p0 minus r minus 1, r into p power 0 minus r minus 1 q into p power 0 minus r minus 2 minus p is 0. The simplification we are doing here, mu 2 dash is equal rp plus r plus 1 p2 square. Mu 2 is equal to mu 2 dash is equal to rp plus r into r plus 1 p square. So variance mu 2 dash is equal to mu 1 dash whole square is equal to rp plus r and r plus 1 p square into rp whole square. R into r plus 1 p square. So rp plus r common is r plus 1 p square, r square p square. Rp r square, r plus 1 r, then r square p square, plus r minus cancel here. Rp square, then rp square. So we are taking here rp is 1 plus p. We are taking the common of the value here. We are taking here. So rpq, the variance of the negative binomial distribution is rpq. As q greater than 1, rp less than rpq. So we are taking less than, mean less than variance here we are taking here, which is a distinguished picture of this distribution. Next week we can discuss the cumulative negative binomial distribution in the next class. Thank you.